Hey there, this is Seth Juarez from Channel 9 coming to you from Building 17, and I'm here with the great Anders Hejlsberg, who not only writes languages, but is a master twister player, from what I understand. How you doing, my friend?
I'm good, and yourself?
So we met, I saw you in the lunchroom, and we were talking about compilers, right, because it's something you like, and you said something interesting to me that I thought we should talk about. You said, because when I went to school, we used this book.
That's right. Well, when I did, we did too,
actually.
actually.
This is the book that you use, right? It was published 30 years ago. And you told me we don't even do it that way anymore. Or you do, but there's some stuff that's changed.
Right. I mean, it's compilers have, a long storied history,
Yeah.
right? I mean, that book, as we were just looking, it's 30 years old, or the first edition was published 30 years ago. And, it's a slow-moving art, but over the last, decade or so, we've become very accustomed to very intelligent IDEs and development tools, and we've become accustomed to features like statement completion and refactoring and go to definition and code navigation and error lists that are automatically populated. Do you know what I mean? And all of that stuff underneath the covers is powered by a compiler. But it's a very different compiler from what they teach you classically to build in school.
It's hard,
it's
right?
been diverging more and more, and there are things that you need to do today when you build these services that editors use that are actually compilers that is just like not being taught anywhere that I know of. And so that was what I was commenting about.
And so that like sparked my interest, right? So I thought we would start today and talk about, okay, how are we taught? And then let's talk about where the gaps are starting to become important. So maybe I thought we'd just draw something up.
Sure. So classic compiler, typically has a lexer, say, and it has a parser, and then it has a type checker, and then there's often then a code generator, say, and then there might be an emitter, depending on and typically we call all of this part here, we sort of call the front end of the compiler, and this we call the back end of the compiler right here. So in comes source text. First, the lexer breaks it into tokens. Then the parser builds what's called abstract syntax trees, or trees, a tree representation of your source code. Then the type checker. Well, then there might be multiple phases in here. It gets a little fuzzier at this point, but typically then you'll build up symbol tables, and then you'll have a type checker that then assigns types to variables and then checks that everything is okay, and then that information in turn then can guide a code generator. Here you may have a different representation that you go into where you build some bytecode, for example, then you can run some peephole optimization on it, and then finally there's an emitter. That's sort of your classic text to machine code compiler of lore.
I see. So
and books, they'll teach you this.
So essentially then this is taking something that we can mostly understand, which is programming language, into something that we're not going to understand.
Right? No. Right over here you have binary executable OBJ files or exe files that the CPU can run, and over here you have programming language text that a human wrote, right? And of course there are more. There might be a linker. There might be all sorts of other stuff in here, but that's sort of the classic picture. And then, these compilers here, often you'll do, after you build, say, all these abstract syntax trees that sort of looks like this, with all your different statements and whatever, and then you may do a whole number of passes over them, and maybe you may even rewrite them into different trees before the type checker, and then the code generator turns this kind of representation into another representation. So there's lots of transformations and lots of work that happens in a long pipeline, and it takes a while to get from here to here, obviously.
Right.
I mean, it can take a minute for
or that's
whatever.
ages, right?
It takes a long time. Now, So keep that in the back of your mind. And then think about now, let's say I'm sitting in an editor and I'm editing my source code, right? Well, a lot of the information I want to know, first of all, I want syntax coloring, right? I want all my keywords to be blue and all my identifiers to be white or whatever. So that's something Alexa can do. Alexa just looks at a little piece of the program. It just looks at right where you're typing, and then whenever it sees a space, then it knows there's a new token, and it's easy to syntax colorize.
Sure.
And if you think back at the history of IDEs, that was sort of one of the first things that surfaced, right? Because, hey, you don't need to, we can do colorization. That's easy. Even when the user's typing, we can get that right.
I mean,
right?
even if it messes up, it's not a problem.
It's not, it's fine, right? It's easy to do, right? But then you also sort of want maybe to have collapsible regions and other things like that, right? And now you start to need more. Now you need trees. You need to understand how all of these keywords combine and where constructs begin and end, so to speak, right? And that starts to get a little more complicated. And then, of course, you'd like to see red squigglies when you make mistakes, right? And when you press dot, you'd like to see, so I type foo dot, you'd like to see a list of what could go here, okay? And, well, you could just show the user all the identifiers that are in the file. I think it's probably one of them, right? But maybe it isn't, right? And clearly, the minute you then select one of them, you might just have made something that's an error, right? So that's kind of pointless. You really sort of want to show people semantically what could go here. So now you need information that was produced by the type checker, right? And you see, as we get more and more intelligent, we need more and more expensive information. It takes, in a classic compiler, it takes a while to type check a whole program, right?
Especially a large one, right?
And the bigger it gets, the longer it takes, right? Yet we know from user studies that if you don't deliver this drop-down in about 100 milliseconds, people start to get irritated. This tool's too slow. I'm not going to use it anymore.
And see, I mean...
and even though here I have a 100,000 line program, and I want you in 100 milliseconds to tell me what can go here, where it might take minutes to actually compile it, right? So how do you do that?
And that's the interesting thing, right? Because before, when I was looking at this, we essentially wrote a binary file that took our code and then just did this all in one pass. And it either stopped here, or it stopped here and said you have an error, or it stopped here. I don't know.
Oh, I mean, the first compiler I wrote, Turbo Pascal, or that I worked on, right, was this whole thing. Not that it necessarily looked like this, but that was, all of it was 32K of code, and that included an on-screen editor and a runtime library as well, right? You clearly couldn't be all that fancy in what you did. And so Turbo Pascal was full of shortcuts, right? Yes, there was a Alexa sorta. The parser didn't actually build syntax tree. It just stopped on the first error. Hey, now we don't have to do an error recovery. We don't have to do a whole bunch of things. We'll just stop and put the cursor right where we were scanning. And then, do you know what I mean? But people expect a little more sophistication today. Right?
So this feels easy up until the moment you start thinking about, like, I'm typing in code and I'm typing dot, but I might not have correct syntax. Sure. I might not have correct semantics here, right? But we still want something to happen, right?
Well, one of the big differences between a compiler that works on your finished program and the kind of compiler that sits behind your IDE is that the compiler that works on the finished program, in a sense, makes the assumption that everything is correct. But sometimes there are errors, but then it just tells you, and then you got to go fix them, right? But the core operating assumption is we're working on correct code. In an editor, your core operating assumption has to be exactly the reverse. Whenever the user is typing something, his code is probably broken right now because he's in the middle of typing. He's not done. Right. So he may have unbalanced curlies. His identifier is not fully typed yet, or he may have an expression that is unbalanced. So your error recovery has to be really good. And you sort of almost have to anticipate what's coming next, and you have to recognize patterns. You may even have to recognize more syntax than it's traditionally valid because you know that users make certain mistakes. And so instead of you just saying error invalid token or whatever, it's much better if you sort of parse out what you think the user will mean here, and then give them a more meaningful error message if you see a certain pattern that people think they can do, but they can't actually do. So sometimes you actually parse more than the permitted syntax just so you can give better errors on it later.
That's interesting. And so is that where the divergence? Because
no, I'll show it. I'll tell you where the divergence comes in. Maybe we have to erase a little bit.
Let's do it
and make some room, and then let's sort of pretend that we are.
So as you're erasing it, is it the case that you have two compilers then? One compiler for when you're hitting build, and another compiler for when you're editing, or are there components of each that sort of are intertwined with one another?
Now, that's a good question, and actually, if you think back on the history, say, of let's just take C# and .NET and Visual Studio and so forth, the first version of the C# compiler, before we did the Roslyn project, so the original C# compiler, was actually written in C++, because we couldn't write it in itself because we didn't have it. It didn't exist yet. Yeah. So, and by the time we'd written it, it was like, whoa, that's a lot of code. We don't want to just like spend a bunch of time rewriting it again. So we actually had a classic compiler. It looked a lot like this. Mm-hmm. And then we had an IDE language analyzer that did sort of some of what we had here before. Mm-hmm. But of course, the two were always diverging, right? And we introduced a new feature in the main compiler, implemented there, but then the IDE was broken because it didn't understand the new syntax, and then we had to go do it again. And so you sort of found yourself doing the work twice all the time, right?
But is it required to do that? I mean,
no,
they're so different.
No, and so that was actually part of the genesis of the Roslyn project. Was we can't keep implementing everything twice. That was problem number one, and problem number two is we want people to be able to take advantage of the incredible insight that a compiler has into your code. So they can write plugins like analyzers and diagnostic tools and what have you, or linters, that use that information to provide even more insights, right? It's pointless to first, every time you want to do something with a C# tool, that first you got to go write your own compiler. Well, most people get off the wagon at that point.
And some people did, actually, because I used to work for a company that wrote their own everything, and they had in memory the whole tree. Yeah. They had in memory all the tokens, etc.
Sure. But it's, as the language gets bigger and more complicated, and that's a lot of pain, right? So we decided basically to build the compiler as an API. And that was what the Roslyn project was about. And we decided to build it in a manner that was engineered to be precisely usable from an IDE, not just as a command line compiler, but also as the thing that is the intelligence engine behind your editor, if you will, right?
So the compiler today in C# obviously is Roslyn.
Yes.
And there must be a common base of just things that, like the lexer, right, and the token, etc. But then where are the differences? Is there differences, or is it just all the same thing?
No, it's the same thing for the command line compiler, and the IDE compiler it's one and the same. The command line driver is just a driver for the
got it.
the service. And then we actually reuse a lot of the same infrastructure for C# and VB. And on the Typescript project, we built it using a very similar architecture, but of course we built it in itself. So we built it in JavaScript because we want it to be able to run wherever JavaScript code runs. But in principle, it's very similar. And so one of the things we do, let's just say for the sake of argument that you're working on a large project. Say a project with 200 files in it, okay? And maybe 100,000 lines of code. And now hypothetically you're typing in some file, and let's see what happens when you want statement completion. So imagine first you have 200 source files, right? So here's a bunch of source files, right?
And 200 is not a lot. I mean, it's average.
Right. Oh yeah. No, we see projects that
we're not trying to
explode.
The thousands.
Yeah. Now, a classic compiler would literally read each of these files from disk, build an abstract syntax tree, transfer, blah blah blah. That obviously is stupid. You don't want to start from scratch every time, right? So you can keep an in-memory representation of a lot of this. So you can load up the source file, and then you can lex and parse each of them into a syntax tree. So you get syntax trees here, and you just keep those around. Because users only edit one file at a time. And that means 199 or 99 of the other files are perfectly fine. Those are fine syntax trees. There's nothing is changing in them.
Right.
Right? But when you have your cursor here in this file and you're typing right here, then obviously that file changes. So one quick optimization you could do here is, well, let's only rebuild the syntax tree for this file every time you're typing something, right? But keep in mind that when you're typing in an editor, in a sense, every time you type a character, you have potentially completely changed the meaning of your program.
Right.
Because you could be right in the middle of typing the name of a type where you have, like some global called foo that's of type, I don't know, bar here, right?
And you can
but now you're typing an S, and it's of a different type, which means everything that says foo dot now has different members, and that could be spread all over your program, right? So it's impossible to do this stuff incrementally. You can't sort of after the fact now try to find all the places where you reference foo and change stuff if you're trying to keep a database of everything or whatever. That doesn't really work out. But anyway, so one optimization you do, keep all the syntax trees around and just modify one as you're typing. And that gets you fast. But of course, syntax trees aren't really delivering the answer when you say foo dot. And now you need to know what can go here. You need to figure out, well, what's the type of foo? Well, it's bar. Well, what members does bar have? Well, bar's an interface, and it's declared which was over in this file and whatever. So clearly, you need semantic information. And semantic information is something that requires you to first be able to look up foo in a symbol table, figure out which foo. There could have been many foos, right? Then you have to figure out its type. Then you have to figure out et cetera, et cetera, et cetera. So it turns out that there's stuff that you attach to symbol. You build symbol tables, and you can build those incrementally as well. But then when it comes time to type check, classically, type checkers have just sort of done multiple passes over the syntax trees and built up all sorts of information. And type checkers typically take a while to produce all the errors in the program. You clearly can't do that either, right? And so what you have to do instead is in a sense, you have to build a system where you can helicopter into the middle of something and say, I need to know something about right here, and I need to know it right now. And then you have to incrementally just build enough information to deliver the answer. Yet later, you may have to do the same for everything. Because the command line compiler, in a sense, it's as if you helicopter into every point in the program and ask all the questions. Do you know what I mean?
Yeah.
Now that is a very different way of building a compiler. And we call that a pull mode model instead of a push model.
I
where,
see.
Often compilers are constructed where they descend down from the top, and they can carry along with them a bunch of contextual information that came from above. Do you know what I mean?
Yeah.
But here, you're helicoptering into the middle, and if you need that information, you sort of have to request it by going up the tree and saying, I need to know something from over here, and that might then cost you to bind something over there. And so it's almost like everything's turned upside down inside the compiler,
I see. So you're in this one node. Say you're typing the symbol foo.
Right.
That node is related to other things inside the tree. Like it belongs in a particular member, which belongs in a particular class.
Right.
And as you request information, instead of saying, okay, let's go to this grandmaster database that might not exist and rebuild it, instead let's just go out one.
Basically, the view we take is that every time you type a character, the whole world is erased. That's sort of the mental model we have, because that way we know that the information we build up is going to be correct with your worldview, and now it's just a question of us getting there fast enough, as opposed to the model of we're going to try to keep a database correct at all times and then go back and back patch and whatever. That's too complicated. I've never seen a system succeed that does that. So instead, we sort of take the functional view of the world that every time you type a character, erase everything. Now let's get back to where we were as fast as we can by reusing pieces of the old data structures. And this is...
that's why they're read-only, right?
That's why they're read-only. So all of these ASTs that we have in memory from all the files that you didn't touch, they're fine. We can just reuse them as they are, right? inside the file where you're typing, we could choose to completely rebuild the AST, but if this is like, say, 20,000 line file, it takes a while to parse just that file and build an AST, but you could sort of know that if you have an old syntax tree for the old file that looks something like this, right? You know exactly where you're editing. You know that you're just editing in this little region there. And you can relate that to the tree, and then you can build a new tree that reuses pieces of the old tree. In fact, when you're rebuilding trees, all you have to redo, if you're editing this node, you could actually reuse all of the nodes in this other tree just by rebuilding the spine going up. The only nodes that actually have to change are these nodes here. And let's say there's a big bush over here. Well, you can just plug that in. And so,
but the thing is, you don't need to edit. You don't need to edit this.
You don't need to edit this
because
or this
you're
or
here.
this or this because you're here. But you need to build a new spine up to the top, right?
See.
So effectively, that means you're just modifying 1, 2, 3, 4 syntax nodes or so as you're typing. And there might be thousands and thousands that you just reuse from the old tree. And now you have yourself, in no time flat, complete syntax trees for your entire program, right?
Wow.
Even though you sort of pretended to start from nothing, but you got yourself your 200 syntax trees back in no time flat. And now you can start binding types to them. And you know, again, you do all of that in look-aside tables. Mm-hmm. So as you're building the type information, you've given each node a unique ID, and you can use that as a key in a look-aside table that you then gradually build up. And then when the user types the next character, you throw all of that away, and then you build it up again if you need to. Do you see what I'm saying?
But so you're only throwing away what you're effectively changing.
But you're lazily building just enough information to deliver the answer.
I see. It's kind of
and
like
then the command line compiler is as if the user just helicoptered into every place and asked all the questions, right? But that's okay that takes longer, right? And that's so now you can see how the IDE, for example, it's capable of quickly delivering answers local to right here. And then meanwhile, because we have functional data structures, we can reuse them even in a different thread and set off a different thread to collect all the error messages by traversing all the trees, you know. But if the user types another character, well, then you just shoot that thread. Okay, fine. Then we'll start again. Do you know what I mean?
Yeah.
And you can reuse the same data structures because they're all read-only. And any new information you keep in look-aside tables that you gradually build up, right?
And the interesting thing about this approach is it's completely sort of, I don't know what the word is, but it feels like it's contradictory. It's like, we have nothing.
Yes.
But don't look under my sleeve because I'm saving stuff too. It's a really interesting approach to saying...
Well, but the thing that saves you here is that it makes it possible for you to reason about the problem.
Yeah.
Because it is as if you started from scratch every time. And that means you're gonna get, if you get the answer right, you're gonna get it right. Mm-hmm. The problem with incremental systems is often that you can't foresee all the various ways that you first get into one state, and then because of an edit, you transition into a third state, another state, and then into another, and then into another, and around, and then, oh, over here you forgot to delete something, and now over here someone picked, and it just becomes this madness machine. Do you know what I mean? But where here, you're just like, well,
it's gone.
It's all gone. Every time you type a character, it's all gone.
But and this is where the contradiction for me lies, but it's not. It's all gone in the context of this, but over here, it's not all gone. We don't care.
Well, it's
leave
not
it
all
alone.
gone, but since it's read-only, it's just the same. You can keep reusing it, right? You just can't store anything in there.
That's interesting.
Yeah. So this is actually, in a sense, that the TypeScript and the Roslyn compilers are huge examples of applied functional programming, because these are functional programming techniques. You know, and these are called persistent data structures.
And lazy loading.
And lazy loading and lazy evaluation and so forth. And lazy, by the way, is also a thing that the minute you have generics in your type system and self-referential types and whatever, it is very easy to construct types that never terminate. So the only way that you can ever reason about anything is by being lazy and by not... You know, like you can construct a type that you can keep pulling on it, right? And every time you ask for a member, well, then it wraps itself in yet another generic type, and then it never ends. So you have to like know not to go there. And lazy systems are great at that, right?
So from the perspective that I've been looking at it and the questions I've been asking, I've been thinking of strictly sort of languages that are not dynamic. So static type languages, that's the word I was looking for. So I'm only thinking of static languages like C#. Are there changes that need to be affected when you're working with a dynamic language like JavaScript with the case of TypeScript?
Well, I mean, I think that the one thing that's interesting about the TypeScript project is that you saw me draw that picture of what a compiler looks like, right? And there was a front end and a back end. Our back end, in a sense, is quite simple, right? We just emit JavaScript. You know, we don't emit machine code.
Right.
And really, most of the usefulness of TypeScript actually comes from the front end and the tooling. And so, in a sense, it's a compiler for tooling's sake, as opposed to a compiler for code generation's sake.
Right.
Which also sort of is a change from how things traditionally were. And then, what also makes it interesting is that it is a gradually typed system, right? Like classic languages like, well, C and C++ and, well, C# and Java, you know, they are basically strictly typed in the sense that everything has a type. Everything has a known type, right? But in TypeScript and JavaScript, well, everything does have a known type, but one of the types is any, which means it could be anything. And now you're sort of analyzing only as much as you want to analyze. But you give users the option to say, there can't be any any's in here unless I wrote them.
I see.
Because then I know what I'm doing, right? But I don't want you to like implicitly have any's in my program. And we have a flag for that. And once you turn that flag on, then we get a little stricter, but then we can also provide more guarantees for you. For example, we can now provide safe refactorings because we know that there are no unknowns in your program.
Interesting.
And that means that we know that we will get all the places where this type is referenced. Because if there's an any, well then when we see an x.foo, and x is of type any, well if you're saying I want to rename foo in type A,
yeah,
but there's also foo in type B, well we don't know which one x is if it's of type any. But if there are no any's, then we do know.
Yeah.
And then we can safely refactor everything. So there are all sorts of interesting things that you never really thought about. And so we're still learning here. You know,
that's an interesting thing, right? Because, I mean, you're effectively taking a dynamic language, adding static typing over the top to help with tooling, but at the same time, you want to be able to do back fidelity as well, which means that your compiler is going to have to be very forgiving.
Well, it has to behave well in the absence of knowledge, which compilers typically don't do. They start bitching at you and tell you, I need to know about this, right?
And that's funny because the compiler that I wrote in school was literally this character token, read this character. And so to me, compilers have always been like very, very strict. And so this notion of, for example, not knowing what's going on when you're changing and obliterating the word, to me is craziness, right? From where I was taught. And then this other notion of compiling in the absence of types is also very difficult for me to understand.
Yes, and that was all of this in aggregate is what caused me to tell you that, well, the kinds of compilers we build are actually like very, very different from what you're taught to build.
So the notions are still there in nugget form, but now your mindset is obviously different with this case and with that. Are there any other things in modern compilers that we build that would be surprising in the context?
Well, I think so. So one of the things we do with all of this stuff, right, that we call the compiler now is, and this is something that we're doing in TypeScript now, and that we've done for C# as well. Is, you know, imagine that you want to plug language intelligence into some editor. Turns out, like particularly in the web space, there are lots of popular editors and lots of people who have their you know, some people like Sublime Text, some like Atom, some like Vim, some like Emacs, some like Visual Studio or Visual Studio Code, or I mean, there's a whole slew of. Now, we don't want to go write like a language service for each of them. Do you know what I mean? So how can we best plug this in? And some of them are I mean, like written in different languages. They're not even
Yeah.
written in JavaScript. How do you plug JavaScript into that? So what we do is with all this stuff, this compiler, is we actually package it in an executable that can function as a command line compiler. But then we have another version of the executable that functions as a language server that you can spin up as a process. And then you can talk JSON to it. And the editor can say to the language service, hey, I'm in this file and I'm on line this and that and column this and that, and the user just pressed dot and I need to know what to show him. Tell me.
Oh, I see.
And then what that process does over there is it's the keeper of all this information. And the editor just tells it whenever the user edits, it just says, oh, the user inserted one more character here and one more here and one more here. And it keeps literally a shadow state of the entire world in a separate process and is ready to serve up answers like that, when the editor needs to know. But it goes through a JSON protocol.
And that's
so they're not even in the same process, these two things. So all of the intelligence actually comes from another program that's running in the background, right?
And that's crazy, right?
And now we can plug that into, all you got to do is implement the simple JSON protocol from your editor extension. And everyone talks JSON, and you can talk JSON in Python or in C or in whatever. Do you know what I mean? So that makes the act of embedding the language into your editor so much easier. And that's why we have such great support in so many different editors, is because we built this thing, that we can reuse everywhere.
And that's interesting, because then you can sort of, as a language designer, you can also be the guardian of the language experience inside any editor.
Exactly. We can actually, and that's why we can release every day a new version. And as long as we have the same JSON protocol for that thing, you just plop it on top in whatever directory your editor extension is, and then now you got the latest language support, because the editor itself doesn't really know anything about the language.
Nor should it care.
Yeah.
And that's the cool thing. So what I'm seeing then is from the old school, right? This is the Dragon Book, as we affectionately call it. We're going from beginning to end. You do it. You see what's wrong, you go back and fix in Vim or whatever old school editor too. Now we're parachuting in information live as we're typing. And if we're in an experience which we do not control, we literally have a service running that does this stuff as well.
Mm-hmm.
That's pretty impressive.
Yeah, that's how. So for example, in Sublime Text and Visual Studio Code, we use exactly the same, it's the same server, tsserver.exe, that just runs in the background. And it's the same one also that you're using if you use the compiler in watch mode and ask it to sit. Then it's a file watcher. It's sort of a simpler version of it that just watches files, and whenever it sees a file on disk change, then it just recompiles. But again, it keeps around all the old ASTs, so it can go a little faster, right? I mean, so...
This is awesome. So where can people go to sort of look this up if they want to learn more?
Well, they can look at the source code.
Oh, that's awesome.
No, actually, it's all on GitHub, right? I mean, so this is all this stuff I talk about. Like the server is literally in the source server subdirectory.
And we're not just talking about the TypeScript. We're talking about the C# compiler as well.
The C# is all, both of them. Roslyn, Roslyn is on GitHub, and TypeScript is on GitHub, and so yep. And the version of this for Roslyn actually is the OmniSharp project.
Right.
That's
Which is the same thing. It's this thing that's running, that's always feeding them. Because I've broken Visual Studio Code, and it's saying, I don't know where the OmniSharp server is. And then I've had to do some fixes, obviously, to make it work. Well, this is awesome, man. Thanks so much for spending some time with us.
Yeah.
We have been thoroughly modernized on the usage of compilers here with Anders Hejlsberg. Thanks so much for being with us, my friend.
You're welcome, Seth.
Thanks so much for watching. This is Channel 9. My name is Seth Juarez. We'll see you next time. Take care.